Hello and welcome to Project 152, your weekly specialist exam prep. If you stick with us every week from now until the end of Term 3, you'll have done every question that the QCAA has ever brought out. Last week's questions, link in the description. Next week's question, link in the description. Go down there, click the link, download the questions, attempt the questions, and then watch the video. All right, so here we go. This is week 5 and the solutions are coming up. Before we kick off, I should say that these first 3 questions, they're relatively straightforward. We're going to motor through them because I have a feeling the last question is going to take a little bit of time. All right, let's go. So here it is, our first lot of vector calculus for this series. An object has this velocity, and we're trying to find its displacement. Okay, so when we're trying to get from velocity to displacement, we're integrating. So be careful, have a think about before you start, am I deriving or am I integrating? Velocity to displacement, I'm integrating. All right, so here we go. There is our velocity function. Now I'm going to do RT, so this is my displacement function. So integrating this, some of us might have trouble integrating those kinds of things, but I'm going to do it pretty fast. Negative 1/2 e to the negative 2ti. All right, now the reason I'm doing it fast is because I know how to do that. I divide by whatever the derivative of that is, and then I'm left with e to the negative 2ti. Now, if you are unsure, if you've integrated and you're like, oh, I'm not sure if that's the right answer or not, what you can do is reverse your process and see if you end up back where you started again. Right? So I'm just going to reverse my process because, like, let's say I'm not sure. Well, the derivative of that, bring the power out, multiplied by the power, negative 1/2 times negative 2 would be 1e to the negative 2t. Yep, 1e to the negative 2t, e to the negative 2t. Yeah, I'm convinced. I feel like I'm pretty right. And then we've got the integral of 1 on t. Now that is a sneaky one. So obviously the QCAA thinks it's a sneaky one too, because they've given 2 answers. They've given ln t as an answer or negative 1 on t squared as an answer. Now, you should know the integral of 1 on t is ln t, all right? And we could check that if we wanted. And formula sheet, yep, there we go. Okay, so you can see that the integral of 1 on x is ln absolute value x. And you might be thinking, why hasn't he done an absolute value? It's because t is always greater than 0. So an absolute value around a positive value is kind of superfluous, so we don't need it. Okay, so the final answer is that. Is it in our list? Yes, it is. C. All right, that's it for that question. Relatively straightforward. On to the next one. Celebrate. Okay, so here's another question. The Cartesian equation for a sphere with center this, this, and this, and radius this is. All right, so it's probably easiest here to talk about what the answers aren't. The answer is not A and it's not B. All right, the reason it's not A or B is because they're showing radiuses, or they're showing these values as being 9. But in the equation of a sphere, you need to square your radius. Right? It's r squared, it's not r. So it must be C or D. And then finally, we need to choose between C and D. And these values here, this +2, this -3, this +4, it's the opposite of what you'd expect, right? So that means that if we have -2, 3, -4, our equation is going to be x +2, not -2. And then we're going to add on our next one, which is y. And you can see it's +3 there, so it's going to be -3 here. And then z, -4, so it's going to be +4 there. And like I said, radius squared, 81. Do I have an answer that looks like that? I believe so. Yes. Done. All right. You're used to that. It all makes sense. That's a quick question. Next. All right. This one could not be easier. We have a complex number, z, and we're told that z is equal to w, right? Now, what is z? Z is a plus 3i. And what is w? It's -3 plus bi, right? And so this is relying on the fact that if 2 complex numbers are the same, the real components are the same, and the imaginary components are the same. So that means that a is equal to -3 and b is equal to 3. All right, do I have an option? -3, 3. Yes, I do. The answer is B. That one was fast. Complex numbers, that was a nice one for the QCAA. All right, celebrating that. Next question. All right, a little bit of vector calculus here. We love vector calculus. What have we got here? An object is projected vertically upwards from the ground, and we're told that its displacement function is that. Determine the velocity of the object through the air in meters per second. All right, so we've got a displacement function. We're trying to find a velocity function. Displacement to velocity we are deriving. So let's do that. Okay, so how am I going to derive that? Well, I guess there's two different ways that we could go about it. We could do this as like a product rule of 5t and 8 minus t, and let that be u and let that be v. But I just think it's going to be easier if I rewrite it, expanding those brackets. So that means I'm not deriving yet, so I've just made it the displacement function again. 40t minus 5t, and all of that j. All right, I feel like I missed a squared there, 5t squared. All right, next up, the derivative of 40t, because now we are trying to find our velocity function. The derivative of 40t is 40, and the derivative of -5t squared is -10t j. All right, I think I'm done there. Determine the velocity of the object through the air. Yep, in meters per second. All right, so there is my velocity of my object in meters per second. 2 marks. What's part B? Determine the number of seconds until the object reaches its maximum height. And so this is an idea that people have a little bit of trouble with, but let's watch my object go through its up and down, right? It's going up, 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 reaches its maximum height, and then starts coming back down to Earth again. The thing to realize is that we actually don't care about its height. We don't care how high it gets. It doesn't say how high does it get. It says determine the number of seconds until it reaches its maximum height. Now, what's the object doing when it reaches its maximum height? It has a velocity of 0, right? Velocity equals 0 at that time. Because it goes up, it goes up. As objects go up and up and up and up, they slow down, they slow down, they slow down, they slow down, they stop for an instant, and then they start coming back down again. So the question becomes, when is the velocity 0? So we just need to solve the equation. 0 equals 40 minus 10t. Yeah, looks like that's it. 0 equals 40 minus 10t. We can put a j in here because that's like our direction, but it falls out. Or rather, I could say, hey, I want a velocity of 0j, 0 in the j direction. That's probably a good way to think about it. So yeah, those j's do come out. And now we have 10t equals 40, which means that t equals 4. Really nice 2 marks. As long as you can understand that when we're trying to find that maximum height, what we're trying to find is actually velocity 0. At least velocity in the j direction, 0. If it was a projectile going like this, it's not its velocity that's equal to 0, it's its velocity in the j direction. It's equal to 0. For projectile motion, we're going to do that a different day. You know, I really should read these questions before I start, because part C says, determine the maximum height that the object reaches. So we figured out that it is at its maximum height at t equals 4, and now I am very interested in what its maximum height is. Now, which of these equations is going to tell me my maximum height? Well, this one right here, because this one tells me the displacement of my object at any time, the position of my object at any given time. Now, I know that it has a maximum height at t equals 4, which means that if I sub 4 into my displacement function, then I'll know what the displacement is at that time, which is when it's at its maximum height. All right, maybe this one. I'll use this one. What I'm saying is I could use that one or that one. It doesn't make any difference. They're the same thing. 5 times 4 bracket 8 minus 4 in the j direction. Okay. So what do I get? I get 5 times 4, which is 20, times 4, which is 80. All right. So I might answer the question with some words. Max height equals 80 meters. All right. I think that's it. This was part A, done. This was part B, and this was part C. A relatively easy question. We're only 10 minutes into the video, and the last question, though, I don't know how long that one's going to take because it is a doozy. So some of you may have noticed that I've changed my shirt. Yes, I have. It's because we're like 5 days into the future now. Because it took me that long to work up the courage to do this question, because it is big. By the time we finish, we're going to end up in a place that looks like this. So lots going on, but all we're going to do is step 1. So what is it? It's a proof by induction, right? This plus this plus this plus all the way up to this term is equal to this nice little formula here. So yes, there's a bunch of trig and stuff, but it's just a partial sum proof by induction question. So you don't even have to think about what you need to do first. You need to do the base case. And so the base case is just letting n equal 1. Now, just for the purposes of our notation and stuff like that, I'm just going to write the following. Let Pn represent the proposition. That just lets us talk about things a little more easily. So what is the base case? It's where we let n equal the first value in our series. Now, what's the first value in our series? Well, it says it's true for all positive integers. So the first positive integer is 1. So we're going to prove true for P1. Let's write something like that. It's required to prove that it's true for P1. Now, what does that mean? It also means that it's required to prove that when n equals 1, the left-hand side is equal to the right-hand side. So that's what this means, right? Now, n equals 1. There's 2 ways that you can sort of do this. N equals 1 means we're doing the first term, right, there. But what I'm going to do is actually sub n equals 1 into that term there. Because when we sub that into there, we end up there anyway. But I just want you to understand that this value here is saying if you sub n equals 1 in there and there, first it spits out that for n equals 1, then it spits out that for n equals 2, then it spits out that for n equals 3, and it spits out that for n equals 4, etc., etc., etc. All right, so it's required to prove this is equal to this when n is equal to 1. All right, so there's the thing I'm required to prove, right? And I've just put 1 in everywhere n appears here. So I've put 1 in there and there, there and there. And on the right-hand side, I've put 1 in there and I've put 1 in there, there and there. Now, when you're doing a proof, even the base case, split it into left-hand side, right-hand side. And once we've got that, we've got to simplify them so that they look the same. So, what have I got here? I've got -1 to the power of 2. -1 times -1 is 1. So that becomes 1. And then here I have cos 2 minus 1. So that's just cos 1 theta. So that's just cos theta. All right. So the left-hand side ends up being cos theta. Now that's not surprising at all, right? Because in the original question, we know that when n equals 1, that's going to be our first term. We're going to end up with cos theta. Don't need the 1 there. Now the right-hand side is always the more challenging aspect of these questions. So I might just tidy this up a little bit. We've got 1 minus, now -1 to the power of 1 is just -1. So I have 1 minus -1. So that's going to be 1 plus 1 cos 2 theta over 2 cos theta. And now the problem is that this does not look like this. There's a problem there, right? And so what are you going to do? Well, there's trigonometric stuff here, so you should be casting your mind all the way back to year 11 and thinking about trig identities, pulling out your formula sheet. So there is a portion of my formula sheet, the right portion for what I'm going to do here. Now, it's not always obvious what you should do here. You're trying to get to here. What's the problem? We've got this cos theta here. What do you notice? Look at things and just try things and see if they work and then go in a different direction. So I'm going to choose the right thing to do from the beginning, but it doesn't always work out that way. You need to be willing to try something, and then if it doesn't work, like make a left turn. What I see is this 2 theta, and that rings alarm bells, right? Double angle identities. So what I see is that cos 2 theta, or cos 2a in my formula sheet, has like 3 different formulas. This one, and this one. And if I peer into the future a little bit, that bottom one, 2 cos squared a minus 1, I think that's going to help me. And we'll talk about why I had that theory after I've achieved it. All right, so it's going to be 1 plus. Now, cos 2 theta, according to this third formula, is equal to 2 cos squared theta minus 1 over 2 cos theta. Okay, so I've just replaced this bit right here with this bit right here. So when I said, like, why did I think this was a good idea? I was going to end up with a cos squared theta on the top when I did this, and I've got a cos theta on the bottom, right? I want to get rid of the cos theta. If I've got a cos squared on the top and a cos theta on the bottom, the cos theta on the bottom is going to hopefully disappear. That was my theory. I didn't see it all the way to the end, but that's what I thought. All right, so 1 minus 1, that's 0. I end up with 2 cos squared theta over 2 cos theta. And then cos squared theta means cos theta times cos theta. So I get to cancel out one of the cos thetas. Those 2's cancel out as well, and I'm left with cos theta. Great. Last line here, right-hand side is equal to left-hand side. And then we can say P1 has been proven. Right? Okay, we are nowhere near finishing this question. All we've done is prove the base case, but that's not nothing. All right, all of this is going to get condensed, squashed down, because we're done with the base case. So there we have our little base case. Hopefully you're watching this on a big screen, because the writing's going to have to be small at times. Okay, now that we've done our base case, you don't have to think next. You know what you need to do. You need to do the inductive step. Okay, show up inductive step. All right, so the inductive step is assuming that it's true for PK. So basically you just rewrite the question exactly as it appears. Just wherever you see the letter N, you replace it with the letter K. Free mark. All right, now that we've assumed that it's true for PK, the next bit, and I don't need to write all this out with my pens, it's required to prove that PK plus 1 is true. So this is the thing that we're trying to prove. And students can find this just a little trickier, but as long as you're careful with it, it's not a problem. Everywhere you see the letter N, you're just replacing it with K plus 1. So I had to replace K plus 1 in K with K plus 1 there. I had to replace it there, being careful to put it in brackets. I had to replace it there, and I had to replace it there. And this is where the fun begins, because this is what we have to prove. Now, luckily, still no real need for thinking, because the next thing you do should be automatic. Taking this equation and just splitting it into a left-hand side and a right-hand side. So up the top here, I have my left-hand side, and over here, I have my right-hand side. And in general, when it comes to proof by induction for partial sums, you're manipulating the left-hand side until finally it looks pretty much like exactly like the right-hand side. Okay, and then I would say that in a partial sum question, the next step also is like straightforward. You don't have to think about it, you just do it. So in a partial sum question, everything from the beginning to here, right, and here is where K is, because this is the K plus 1 thing. This is the kth thing. Here, you take your assumption, right? You take the right-hand side of your assumption, and you take it and you put it right there, right? That's our next step. So we're just taking this piece and we're putting it right there and just replacing that big long sum with that little piece of our formula. Okay, so that's that job done. So looking at what's happening here, see this pink stuff here? That's being replaced with just this piece here. And everything else is what came after it. All of this stuff right here. Hopefully that makes sense. Okay, what could we do here? What's next on our agenda? Well, look at your right-hand side, right? It's a single fraction. So, it might be nice if this was a single fraction. All right, so that's one thing to keep in mind. The other thing to look at here is that, there's a little bit of work that we can probably do here just to make our life easier, right? There are some simplifications that we can do just, right off the bat. This k plus 1 plus 1, and this, bracket that says 2 bracket k plus 1 plus minus 1, things we can do there. All right, so let's do that easiest thing first, which is just simplifying some brackets and things like that. All right, now, again, I'm not going to get my pens out. I am going to do that later on. You can see that k plus 1 becomes k plus 2, and this thing here, 2k plus 2. And then there's that, weird negative 1 on the end. But that's been accounted for in 2k plus 1, right? Because this is 2k plus 2, and then I subtract 1. I'll end up at 2k plus 1 times theta. Okay, what was the other thing I said? I'm aiming for a single fraction. So it would be really nice if this was a single fraction. Now, adding fractions is something you've been doing since year 8. All we need to do is make the denominators the same. So this one has a denominator of 2 cos theta. This one needs a denominator of 2 cos theta. And so to do that, I just multiply top and bottom by 2 cos theta. All right, let's take a look at that. All right, so multiplying top and bottom by 2 cos theta gives us something that looks like this, right? And then I can add that fraction to that fraction, and it's going to be nice and neat. We don't have to think too hard about it. 2 cos theta, and then everything just stays the same as it was on the top. Now, a lot of people in specialist maths are going to be tempted to skip this line and skip this line, etc., etc. And with fairness, you probably could skip this line, but you're probably also going to mess up, and then you're going to have to spend an extra 10 minutes figuring out where you've messed up, and you can never get to here. So, something to keep in mind. If it's just 10 seconds to write something out, you're not going to save time if you skip it. Okay. This is where it gets really challenging, right? Because I'm looking here, and there's all sorts of stuff going on. And so this is where you really need to start thinking again and going, okay, there's trig stuff, there's loads and loads of trig stuff. I can probably simplify it. Trig identities can probably help me out with that. So this really is where you pull out your formula sheet and you look around for stuff that might be useful. Now, I've already done that, and what I've noticed right here, right, this bit here, cos 2k plus 1 theta times 2 times cos theta. Let me just write that out. All right, so I've just written out a small portion of my working, and this is a good technique. You've got blue paper in exams, you can use that and scribble on it. Okay, what do I notice? I notice that I've got cos of a thing, which I can call A if I want to, and I've got cos of another thing, which I can call B if I want to, and I have a 2 here, right? Now, that says this times 2 times this probably makes sense for that 2 to be out the front. All right, so our product identities say that if we have cos of something times cos of something, we can rewrite it a little bit differently. So it's going to be equal to 2, because that 2's still out the front, and then half. If you're not sure where I'm looking at this cos A, cos B, the second one here. 2 times, and then this is going to be equal to 1/2 of cos A minus B. So cos 2k plus 1 in brackets theta, and then minus B, minus that theta. All right, so there's sort of our plan, but then we're also adding cos of A 2k plus 1 in brackets theta plus theta. Okay, so just double checking that we agree with my second formula here. This is equal to half of cos of A minus B, okay, plus cos of A plus B. Now it feels like that's right. Okay, good. Now, obviously the 2 times a half, they get rid of each other, so that's nice. Now, what does this piece become? this becomes cos 2k times theta, so 2k theta, plus theta. Right, 2k times theta is 2k theta, 1 times theta is theta, and then minus that theta on the end. Oh, that's nice. They're going to cancel out. And then we have cos 2k times theta plus theta plus theta. All right, very nice. Now, this piece here, it becomes cos 2k plus theta minus theta, which is 2k theta. And this piece here becomes cos 2k theta plus 2 theta. All right, now it probably makes sense, right, to like factorize this in some way. So why don't I write it as 2k theta plus cos, common factor of 2 theta, I think, and then k plus 1. Something like that. All right, let me hide over here for a second. So what have I done here? I've done a whole bunch of working that it only pertains to this piece of it, right? So I'm imagining in an exam, I would kind of write this out on my blue paper maybe, or like somewhere off to the side, and then use this result and plug it in to here. And that is what I'm going to do right now. I'm going to use this result and plug it in to there. All right, so let's bring that down. Okay, there it is. So you can see I've plugged in my result right there. Now the only small change is that here I wrote 2 theta bracket k plus 1, whereas here I wrote 2 bracket k plus 1 theta, but that's just changing the order of the multiplication. Okay, that's where we've gotten to. Let's get rid of this. Let's keep going. All right, so it's not like super immediately obvious what you should do here, but if we take a look, and sometimes you just got to try something. If we take a look, there's not much happening here at the moment, but what we then have is negative 1 to the power of k plus 2, and then that gets multiplied by everything in that bracket. And there are actually 2 terms in that bracket. There's cos 2k theta, and there's cos 2k plus 1 theta, right? So if that is being multiplied by that and that in the set of brackets, we can expand. We can multiply this by this, and this by this. All right, so let's do it. Let's go for our next line here, which looks something like this. So negative 1 cos 2k, and then negative 1, and then this thing. So we've just expanded that bracket. Simple stuff. Now this next bit is going to take a little bit of a leap of logic, but it will get there. All right, so let's just move this thing out of the way. Just give us a bit more space on our screen. Now we have 1 minus 1k, and then cos 2k theta, and then we have this thing here, and then we have another cos 2k theta. And then we have all this other stuff here, right? Now, let's just look at cos 2k theta, and I'm going to just let cos 2k theta equal x. Doing this allows me to just like simplify the thinking here, right? Again, I'm probably doing this on my like little blue paper or something because I'm not sure where this is going to lead. All right, so what does this end up looking like? It looks like 1 minus, and then minus 1k, and then x, and then plus negative 1k plus 2 cos, or not cos, x. So hopefully you're following. What I'm doing is just a portion of here, right? I'm doing this portion here for now because I think it's something special is going to happen because I'm noticing 2 of the same cos thing, and I've just let them equal x. Okay, negative 1 to the k. Okay, what's negative 1 to the 1? That's negative 1. What's negative 1 to the 2? That's positive 1, right? What's negative 1 to the 3? That's negative 1. Negative 1 to the 4, positive. Raising negative 1 to the power of k just oscillates. All right, it oscillates from negative 1 to positive 1, right? So if negative 1 to the k is something, and negative 1 to the k plus 2 would be equal, right? Because negative 1 to a power oscillates it from negative 1 to positive 1. Going from k to k plus 2, these are going to be equal. This is equal, right? So if this was 1, because negative 1 to the 2, let's say k was 2, if this was 1, what I'd have is 1 minus 1x plus, and this would also be 1x, right? And those x's are going to cancel out. Now, if this was like negative, I'm just going to end up with the opposite. I'm just going to end up with 1 minus negative, which is going to be positive, plus negative, which is going to be negative, and then they're going to cancel each other out again. This is an amazing thing because the x's, which are not x's, they're cos 2k thetas, because of this power of k and power of k plus 2, they cancel each other out. Now, if that felt a little too hand-wavy, we can do it a bit more academically rigorous, mathematically rigorous. We can just write negative 1k x plus, now this can be split up into negative 1k times negative 1 squared, and then x. Now, what do we end up with here? We end up with negative 1k x plus, now this is still negative 1 to the k, but negative 1 squared ends up being 1. Alright, and then because we're multiplying, move over here, because we're multiplying by 1, that kind of cancels out. So we're just left with x there. And now you can see that this and this will cancel each other out. Minus that, positive that, we're left with just 1. So why have we done all of this? Because now in our formula, we have a 1 out the front, and then this term and this term are going to just disappear. We're just going to be able to cancel them out, and we're going to be left with 1, and then this bit on the end, and we're getting super close to that. So it ends up looking a little like that. All right, let's get rid of the blue stuff. We are so close. So at every stage, you should be looking at this, and constantly evaluating, like, okay, how close am I? What do these have in common? What's different, right? And so when I look at this and I look at this, I see two differences. I see a 1 plus here, but I see a 1 minus up the top. And then the other difference is I see this one as a negative 1k plus 2, and I see this one as a negative 1k plus 1. So then, and that's it. That's the only differences. So the question is like, why have I got these two differences? And like, how do they must cancel each other out in some way? Like something must be happening there. All right, so how can I finish this off? Well, if I look here, I have a 1 plus negative 1, and then instead of having it as k plus 2, I can have it as k plus 1 multiplied by negative 1, right? Negative 1 to the power of k plus 1 times negative 1. That's the same as negative 1 to the power of k plus 2. And then just the rest. Okay, so this bit here now becomes 1 plus all of this, like, because that's all stuck together with this multiply. So that means that this, with multiplying by negative 1, becomes negative. So it becomes 1 minus negative 1, k plus 1, done. And we can put that here. Let's do that. All right, so that's it. I've put it in there, and look. We should be super happy now because that is equal to the right-hand side. Like, we are like done here. It's super awesome. So I like to put a little statement afterwards, something that looks a bit like this. True for pk plus 1, if true for pk, true for p1, therefore true for all of the positive integers. Okay, that is that question. That's it. That's all of it. Done. You know, you might be saying, well, hang on, he did like 3 steps and then he deleted those steps. You're communicating to a specialist teacher, so you don't have to show every single step, but you do need to show enough steps. Now, this was worth 6 marks. 5 marks for various stages, but 1 last mark for communication, for organization of your work. So if you're looking for top marks, there's always a couple of marks in these exams for your organization. And so this is your opportunity, or this is the question that they selected to say, if you're organizing it correctly, if you're making it clear what you're doing, we'll give you a mark. If it's all over the place, then you won't get that mark. So something to keep in mind. I don't think I've ever earned this more. Alright, those were the week 5 solutions. Bump. Next week, we're on to week 6. That comes after 5. We're back to Tech Active that week. So hopefully you're getting a theme that we're looking at our calculator when we do those Tech Actives. But go into the description, download the week 6 questions. Catch you next week.